here, and thank you for coming on this cold winter morning like this. The other mic. Now there are three microphones on my desk. Not even the president has so many mics. By exclusion, it should be. All right. Okay. Thank you for coming here on this cold winter morning. Perhaps during your holiday term. As a reward, I promise you, I won't be boring. Okay? So, again, thanks to a lot of people here participating in the organization of this Brazilian taxpayer-funded event. What are we talking about today? We're talking about sustainability. Most of you, when you turn on TV or turn on YouTube, you think of sustainability, you maybe think of Greta Thunberg. No. Sustainability means electricity bills, right? That's environmental sustainability. Then we talk about another aspect of sustainability, which is the social aspect of sustainability. But we are engineers. How can we do something like that? What can we do in this respect? For the next hour, you will see my beautiful face, so I think you should know who I am. Alessandro Simeone, Italian, of course. Currently, I am an associate professor at Polytechnic of Turin. I hope you will visit it. We have many exchange mobility programs for Brazilians. USP agreement we have. Before that, I was working in China. I was an associate professor there. Different planet, right? A very nice experience. I came back with wife and daughter from there. So. Before, I was a research associate in Loughborough University for 3 years, just enough to learn how to pronounce that name. And before, I was a student in Naples, where I met this young fellow here, Professor Olivier. So, that's myself. Today, we need to talk about some social aspects of sustainability, right? Something I particularly care, which is the health and safety, right? You are particularly aware that factors like lack of health and safety measures, lack of rules, right, worldwide, technologies which are sometimes too difficult to understand for workers, and above all, at least in Europe, I don't know here, but yes, so the aging population. Our workers are getting old. That's dangerous. Still, we need human labor still in factories, right? On the other side, we have technologies, wonderful technologies. You work on it, right? You develop sensors as your job. You design sensors, you design fantastic embedded systems. Can we use them to improve the social sustainability conditions in terms of health and safety, for example, right? Well, I guess so. Most of us have smartwatch. This is already a good step, commercial step, right? Why we need to do this? Because it costs money, and above all, it costs human lives. It's a serious issue. It's a serious issue in our field, which is industrial field, not to mention other fields like construction workers, which is even maybe worse. So, investing in health and safety is clearly an advantage. Again, we are engineers. Why do we care about this? Because we want to develop some technology for that. And this technology must be useful for the workers, but convenient for the companies. Wow, that's different, right? And then, this is expected to boost the social sustainability conditions, right? How do we call this? We call this Industry 5.0. Why? Because it's a sexy name. Technology belongs to Industry 4.0, which is true. Well, let's add the human factor, and let's call it 5.0. Now, okay, we are engineers, we want to do something in this respect. What can we do? We can develop a human cyber physical system. pretty pretentious job. And why do we want to develop this? We want to do something, we want to use human cyber-physical system, possibly intelligence, so using machine learning, artificial intelligence, to monitor, assess, and why not predict health and safety conditions, right? Risks. And now we use words we are more familiar with. We want to develop a model that dynamically estimates health and risk conditions. Also risk priority, for example. We want to facilitate early detection and this will, and detection of hazards. And act, so implement right measurements. And this will improve, is expected to improve, the overall social sustainability. When we say sustainability, right, economic, environmental, not today, no, not today. Today we don't go by social, in particular health and safety. There are other aspects of social sustainability, jobs. Maybe they're engineers or jobs. We barely find ourselves a job here, right? We want to focus on risks, various types of risks. We will analyze them, okay? Some of them you know, you're familiar, physical risk, biological risk, unless you're involved in food manufacturing, or ergonomic risk, you work in an office 9 to 5, you know what I'm talking about, chemical risk, factories, safety risks, right, we'll see what this means, mental risk, and that's another big chapter of research. Now, okay, cyber-physical system, human cyber-physical system, there are some hundreds of books, hundreds of papers with hundreds of definitions. Anyway, we want to integrate computational entities. Oh, we are very good at that, right? We program, we do everything. With connections, right, to the surrounding physical environment, the factory, right? So, computer and factories. But what is the human, right? We need to consider the human, and we need to embed the human aspects here to dynamically interact with machines and with the environment. This interaction, if properly modeled, can help to reduce risks, but many other things, right? Okay, beautiful definitions. We can read many definitions. How does it look like? What's the phase of the human cyber-physical system? What's the phase of the human cyber-physical system that is able to help in improving health and risk conditions? That's how it looks like. Huh? So this is the phase. What do you see here? Layers. Layers of what? Well, different type of layers. First of all, if we want to improve something, then we need to measure it. All right, we need to measure humans, we need to measure environments, we need to measure machines. We're very good in measuring machines, aren't we? Right. For this we need sensing units. Most of them are commercials. Fine. And some of them are very cheap, very small. You can embed them everywhere. Some of them instead are more difficult. Right? Wearable sensors. Cristiano Ronaldo uses them, not the factory workers. But thanks to you, in a few years, everybody can afford them. That's what you do. You develop sensors. Okay. That's your job, right? Fine. So these sensors are very good in monitoring human health, many data, working environment, right? But also machines. If we know how to measure machines and how the human interacts with machine, then we can really make a step forward. Okay, what do we have now? Data, a lot of data, streams, numbers. Well, we need to process them, and now this is different. Machines, sensors generate data. We need to transform data into information, we need to process them, right? And there are many other. Of course, there is a network layer here. You also very expert, so I will not spend time in boring discussion about Bluetooth, LAN, and WAN, because I assume that you all know how to collect various types of data, diverse type of data, how to convey them into an analytic layer, which is cloud-based. Clearly, we can imagine a fog level for preprocessing, make everything faster, and we need to process loads of different types of data to extract information. How do we do that? Well, there is a procedure that I will explain. And it's a data fusion. It's a fuzzy, logic-based data fusion. But we're engineers, right? So we need to process human health data, working environment data, to get information about risk. Your expertise is no longer enough. We need to borrow expertise from working, occupational health, psychology, and any other boring stuff. This data fusion enables a modeling of risk. We'll see what's the face of this. Fine. This inputted into machine learning algorithm is able to model risks. Now, the word risk, again, is no longer enough. We need to break it down. Different types of risk, as we saw in the slide before. So, if we know the risk, and if we know what type of risk, right, what can we do? We can enable an application layer. So we can make an intelligent diagnosis which will understand what are the risks and perform corrective actions. This works. I will show you. So this is the concept of human cyber physical system. This physical system is the factory. The cyber is all this computational stuff, and the human is the goods. We are measuring human and looping on human. Okay? That's the most important thing, the most important message I want to tell you. Clear. According to the various type of diagnosis, we need to perform a personalized measurements, common measurements. These come from manufacturing engineering, so performing maintenance, assisting operator, we do the scheduling already, but we need to get there. And we'll see how. Again, we need to measure a lot of human health data. Most of these variables, which are not mentioned because it will be boring, but they are measurable with commonly commercial available devices, right? Smartwatches, smart sensors, but really, you can buy on Amazon most of these. Okay? Some of them are very easy to measure, some of them are slightly more difficult. What are you waiting for? Can you develop something cheaper and easier to use to monitor the respiration rate? Please, that's the most expensive sensor we got. We're waiting for you to develop a cheap one, which won't possibly. Right? Working environment, look, some of these are very easy to understand and to visualize. I'm talking about the noise, talking about presence of chemicals. We developed gas sensors. Yesterday we saw some gas sensors. Ambient temperature, airflow, right? Radiations, noise. These are all things that interact with the human health. Badly. What about the machine? Our first look at there, right? We have vibrations, we have process parameters, we have acoustic emissions, so all data coming from the machines. If a machine vibrates, and for 8 hours you're next to it, right? That's bad for the health. So, here, we contributed to the process monitoring literature, and there are many data which are available. Okay, we have human health data, we have process environment, and process machine data. We have all of them. The more the better. Well, really, depending on the factory we're talking about, right? There are many variables that you can monitor, you can ignore, depending on the context, right? This is the architecture, so human health can be measured online, but also offline if you have a history of high blood pressure or cholesterol. Clearly, this is important, you don't measure it online. So I need to record, which means I need to disclose some sensitive data. The system administrator can potentially know about my health before I am aware. Again, we're not lawyers, we're engineers, and we don't care. Right? We have different kind of technologies for data transmissions. We store in the database, cloud database, available to everyone. I can visualize some of this data on my phone as well, on my watch. Now the things get difficult. What do we have? A lot of data. And we don't know what to do with them. So we need to transform high number of big diverse variables into risk. Well, it took us months to develop this framework. And this is the concept. Look, physical health, working environment, manufacturing data, we need to fuse them. This is a sensor fusion, where all these lines are fuzzy, logic, inference. Are you familiar with fuzzy logic? If it's cold and if it's windy, then we'll reject. Well, easy to say, difficult to model, because if the blood pressure is 80 millimeters of mercury and the workshop temperature is 36 degrees, and if the machine is vibrating a lot, then the risk is unknown. An engineer, I don't know what I should put into that inference. That's why we need to do it recursively by grouping similar variables based on a knowledge base, which is not only an engineering knowledge base, but it is in medicine, occupational health, psychology, physiology, and whatever. And process engineering as well. At the end, we measure, we build actually our own risk indicators, not only risk. It's not enough. Physical, biological, of course, ergonomic, chemical, safety, mental as well. So, the concept is easy. It's difficult to understand what's inside this. What are the inputs? What are the rules? What are the outputs? It took us months fine-tuning this with the books of occupational health. Difficult to understand for us. But we managed it. And I will show you. This is the fuzzy process. Look. Some are familiar, some are less familiar. You have a number of inputs, you need to falsify. 20 degrees outside, is it hot, cold? How is it? Is it 80% hot and 20% cold? Right, you need to falsify. You need to set the rules, this is difficult. If the temperature is high and the machine is in overload and you have high blood pressure, then an output is a certain value. Right, the output is again a fuzzy output. We need to transform into a number that we're able to understand. And this is the defalsification process. Long process, difficult. Breakfast with the coffee and MATLAB for months, with years. Right? And then what can we do with that? Once we know that the risk is 0.3, what can we do with that? With that we do, right, a classification with generic machine learning algorithm. You're familiar with neural networks or support vector machine or whatever you have there. Right. What we want to do is to understand if the risk is low, medium, high, and its priority is low to medium, high. Right, there is a long process of training that I will spare you this morning, but I want you to understand that we have a two-phase classification to understand the priority and the magnitude of the risk, and time of risk, of course. And then, what's the root cause analysis? Is this a risk coming from the operator itself, because it's sick? Is it a risk coming from a machine? Is it a risk coming from operator and process interaction? That's what we do. And we know this using non-invasive sensing units. So a lot of computational stuff, cheap sensors, big output here. Right, that's the concept that I'm explaining. Can we use it? Can we use it on a real factory scenario? Think of this. We have a process flow here, an annealing process. Well, we are building this. This is just a metal sheet working. There is an operator working on the annealing, so thermal process. There is another operator performing the deep drawing, right? Another operator performing another annealing, and then another couple of operators doing the etching and finishing, working on chemical stuff. They're subject to various types of risks, right? All day long, 8 hours. Right, imagine a factory now with this configuration, okay? What can we do with that? Well, first of all, we schedule the process, right? We know everything about the process, so we have all the operations for all the operators, we have the cycle of activities and the time. We know this, we design it. For 1, 2, 3, 4, 5 operators, 5 processes, each process made of several activities, which take some time. Okay? Let's consider the best case scenario. Young worker can be one of you. Okay? Healthy and fit, no clinical background, the factory is perfect, good conditions, ventilation and everything, and all the machines are perfectly functioning. So this is heaven, right? What happens in this case? We measure what we want to measure here. These are the physical variables, the physical health variables, environmental variables, machine variables according to the classification I showed you before. We normalize them. What does it mean? The temperature 20. The temperature, if the temperature is 20, then the temperature is good. That's the classification process. Normalization. And then we need to build our risk factors, right? Respiratory risk, heart risk, vascular risk, eyesight risk. Ooh, man, this takes time, right? So, but we pass from 59 variables to, I don't know, 20, something like this. So we're fusing them, we're reducing, we are building risk indicators. Finally, we can, well, I spared you some middle passages here, otherwise we'll stay here until tomorrow. And we build our array of risks. So risk is not one number, it's a multi-dimensional space, 6 dimensions. Okay? And here we are. But we can even go further and do one overall risk that I can visualize, something that rings when those values are out of control. Well, this part is hard. Okay? After 1 year, we are still doing experiments. We are still refining, we are still tuning, we are still developing. But the concept is here. Okay? 1 layer of normalization, 1, 2, 3 layers of fusion. These are all soft work, okay? Soft work. Fuzzy logic based. The results of that. Well, let's make it easy. Let's show with the overall risk. How does it look like? Look, I'm working for 480 minutes, and the overall risk, which is the only one easy to visualize, is this one. You can see there are peaks. Peaks correspond to dangerous operations, dangerous activities. What happens here? Well, this is the lunch break. The risk is not 0, that's the minimum, right? So, regardless the number, which here I normalize between 0 and 1, I can see that there are peaks, and those peaks are what I care. Well, there's also a pie diagram here. What happens here? Well, here I can see the share of which risk type is more important. Is it the physical risk? Is it an ergonomic risk? Well, I can do this in real time. And it works. Of course, here I'm showing you a demonstrator of this system. And again, I told you that the overall risk is not enough. I need to know all of them, right? And I have the trend of each of them. So I can break it down per type, in time, over time. And that's what I do. Okay? I can see, for example, that this particular process has some physical risk issues and some ergonomic issues. I can afford to not care about chemical and safety. Safety is touch something very hot, something like that. Right? 2. Right, that's what I do. And that's what I need to care. What can I do? Oh, well, of course, I can do this for all the operators, right? I will not show, but I can do this for all the operators, for all the machines. Let's suppose now that there is a problem. Let's suppose. In this process, there is a malfunction, a generic malfunction. For example, I notice an anomalous level of mechanical vibrations, right, and noise. Although such issues do not have any significant impact on your workflow, I notice at relevant time interval changes in body vibrations, hand arm vibration, noise, mechanical vibration from the machine. What happens? It happens that when I do the intelligent classification, if before I was in the blue scenario, low risk, now with those changes, I get here. Is it high risk? No, it's not high risk, but it's a medium risk. And it's a medium risk that I need to classify, I need to understand where it comes from. Well, I put all the data into the intelligent classifier, or alternatively, if I don't have any chance to train, I perform a root cause analysis. Are you familiar with the root cause analysis? Right now, many harmony. I try to understand the reason why something happens. Or I can do this, and with this I can train a machine learning classifier. Well, what I understand here is that in this very case study, there is a problem with the lubrication system, and I need to perform an extraordinary maintenance. I'm bringing you a very easy case study. I just want to let you understand the principle. Right, before the corrective action I had the orange line, high during the whole time. After the corrective actions, well, the machine doesn't vibrate anymore, right? The noise diminished, the risk decreased, and I reached my objective by implementing an extraordinary maintenance. Now, this is clearly something big, right? But do I really need all of this to understand the cause? Well, I show you a simple case study with some immediate reasons that you can immediately visualize now, right? But there can be some hidden causes that you can't visualize immediately. But this system detects everything. It really does, if properly tuned. Let's see now what happens with a high-risk scenario, right? There is an exhaust fan problem. That's a big problem, especially if the alarm system doesn't work. Exhaust fan failure, and you don't know. The air becomes unbreathable. Right? During the particular process, during the chemical process here, right? So this causes a build-up of hazardous gases, fumes. So what can I detect? The fan energy consumption. The fan doesn't work. But I'm monitoring the energy consumption, which is reduced. There must be something wrong with that. Priority compounds concentration in the air as well. You develop gas sensors, so you can teach me about this. But also an ambient temperature increase, for example. Look, here we have the low scenario with the high risk scenario. The high risk scenario has been basically estimated by changing, because the values of the variables we saw before increased. The risk increased. And what can we do now? Well, the first thing to do is try to swap the operator, right? Because we don't know yet. I swap the operators. There is an algorithm to understand which are the best operators to swap, right? I swap operator 4 and operator 5, and I can see that it's not a problem of swapping. So it's not a personal problem. So I need to perform another root cause analysis, but if I have enough data, I can do it intelligently using machine learning. Well, and I understand there is a problem in the ventilation system because of the obstruction of the duct. So I have a clogged duct. Well, I perform maintenance, right? I read the measurement, I remeasure, and what I can see is a drastic decrease of the operator risk. And this, of course, for these results we have seen, we didn't use 59 variables, we selected only the important ones, because we have some sensors not completed. And these are the results, right? So it's able to detect, and it's responsive to changes of the environment. Where can you find more information about this, including boring parts of the algorithms? And here, these are my 2 papers. Right, here we have the references, and here we have the QR code, risk assessment, but also risk priority modeling. So it's a research theme that we are still carrying out, and I have students, master students, and PhD students continually working on this. Okay? If you find some overlapping of themes and interests, we can go on with it. We can bring you to it, we can send you someone here. The most difficult part is to convince your boss to send you to go I think he needs you here. So, fuzzy logic as a tool to estimate something from a variety of data. Can we use it for something else? I mentioned physical problems, ergonomic problems. What happens if you have a mental problem? And this is a paper I'm very proud of. I'm going to present this at the end of the month in Greece, the CRT General Assembly, and you know how hard it is. Where there are people who are less lucky, and they are neurodiverse. Unfortunately, they are unemployed. They are unemployed. Can we use technology for helping them? Can we use technology, human-machine collaboration, reciprocal learning to help these neurodiverse operators to be efficient, right? Like us, right? The hypothesis is yes, we can. And we can do this using human-machine collaboration and reciprocal learning. You heard of machine learning, you heard of recurrent learning, you never heard of reciprocal learning. I would say. So, we want to integrate neurodivergent workers, in this case workers with memory problems, using non-intrusive way to measure their cognitive load, which is what we need to measure to let them work. And we will use machine learning to enhance also their task performance. Right. This is the framework. Again, measure everything, like before. Measure process, workplace, physiology, and behavior. Estimate using the similar approach, like fuzzy logic, to estimate their cognitive load, not only stress. What component of the stress of the cognitive load we need? Okay? Now I'll show you all the things related to memory. A machine learning classifier will tell us if the worker is suitable for working, or he needs technological support, or he needs medical aid. We focus on the technological support because that's really key, right? And then performing reciprocal learning will help this neurodiverse worker to be efficient. Right? Look at this. This is very similar to the fuzzy structure multi-layer I showed you before. Right? These are all the variables that we could measure. We measure only the green one, right? The body depth, so some physiology, some manufacturing process, and some working environment. We built recursively, right, the cognitive load factors, and of course we focus now on the cognitive load dimensions, which is the memory. And this is the reciprocal learning. Okay? What can we do with those results? Here's reciprocal learning. So here we have 2 loops, the green one and the orange one. What happens? I'm working, I'm doing an assembly job. If I do some mistakes, we have image recognition, normal image recognition, based on deep learning, right? We have a system which detects the errors, right? What's my problem? Memory. Okay, so when I'm performing an assembly task, I forget the operation. Right? Still, as a human, I'm able to recognize the pieces, the components. On the other side, we have the computer, who is very good in remembering the sequence, but struggles in recognize. If you do some object recognition, we know what I'm talking about, right? Right. I will not get into these details, but we have human in the loop, right, and machine in the loop. So human in the loop, the human provides feedback to the machine output. Look, dear machine, this is not a phone, this is a bottle, right? Easily, I recognize it easily. But I forgot what to do with this bottle. So the machine in the loop tells the operator what is the right sequence. The machine teaches to the human the sequence, the human teaches to the machine the piece, the components. That's why reciprocal learning. Case study, right? Here we have, oops, sorry. In general, assembly case study. A gear, right? That's a gear with some steps, here with 10 steps. One phase is manual and the second can be robot assisted. We have some components, and this is, I need to show you, but that's it. That's how long it should take. But if it takes longer, maybe something is happening, maybe you forgot what to do. Right, trigger, okay. We do 3 scenarios. First scenario, no error, right, as it should be. Second scenario, error with manual correction. What does it mean? I did some mistake, I call my supervisor, the supervisor comes, inspects, tells me what's the problem, tells me what to do, goes back, check again, right? Takes time. The other one is the error with the reciprocal learning correction. So 3 scenarios. Here we have all the times, all the step times. If you're interested, I give you the link. This is the experimental setup, collaborative robot, right? This is the camera that detects the error, this is the interface, control box and everything. Nice. And here we have some results. Look at it. This is how long it should take in case of no error. Right? Here instead, we simulated 2 neurodiverse errors where the operator forgets memory words. We cannot use real neurodiverse operators because we need to fill a lot of forms. So unless we have volunteers, it's difficult. Right, look. Error, I call the supervisor, this is when I realize of the error, this is when I call the supervisor and fix the error. The time, very long. Here instead is when I use the reciprocal learning approach. The error is immediately detected, the robot gives me the right part, and I save time. So we have a time saving here, but look at the error. What is this? This is a cognitive load. You can see there are some easy operations, lower cognitive load, more difficult operations, very high cognitive load. If I'm doing a mistake, I go under stress, and my cognitive load increases a lot. Increases to unidentified level of working. Right? I need to go to the supervisor, I'm afraid of the supervisor, anxious, anxiety. Instead, if I have a reciprocal learning system which tells me what I'm doing wrong immediately, and the robot gives me the right path, I don't have time to be anxious, and the cognitive load is reduced. Right? I can forget the sequence, the robot knows the sequence, the robot doesn't recognize this. And it's difficult also for you. These are 2 wheels, one with 40 teeth, one with 45 teeth. Very difficult for a machine. For the man it's very easy, because one is small and one is bigger. Very easy to touch, right? That's why we use this system, right? So, the system recognizes basically everything except those 2 gears because they are difficult to classify. The man sometimes remembers, sometimes forgets the sequence, but the robot helps. And this is what I wanted to show you because look at this, right? This is the system demonstrator. This is my PhD student, right? This is the real-time detection. Look at there. And here we have immediately start. This is the prompt with the messages. I'm acquiring a lot of pictures. These are the reference images. If I'm doing any mistake, then the system recognizes the mistakes and the robot gives me the right part. Now, it's still slow. It's still slow. We need to increase the speed, we need to improve, we need to refine, but it's there. Okay? It's there here. I will make sure you will have a look. This is the robot, take the right part and bring you the right thing, right? Bring you the right component so you can perform your assembly sequence correct. Right? I will give you the link for this paper. One last case study. This is when you have memory problems. And when you have reading problems, what happens? Because here you can see the results on a screen, right? You need to read. And if you don't know how to read, if you have some dyslexia, right? That's how dyslexic reads. Difficult, very frustrating. And imagine if you need to read assembly instructions with this. It's going to be painful. What can we do if we cannot read them? So, we need to reduce the cognitive load coming from errors due to reading problems. Right? How? Providing digital instructions. Again, but digital instructions, what can I do? I cannot read. I have a headache after 10 seconds. Well, I give you them in your headphones. Sound messages. Right. How? In this way. You work, you read the instructions, but you can't. Right? So you do some errors. Well, we have a system, camera. The camera recognizes all the possible errors you can do. You take the wrong component, you take the wrong sequence, you take the wrong tool, you perform the wrong operation. What's the result of a deep learning classification? It's a confusion matrix. But if it's a confusion matrix, I know what it should be, and I know what it is, right? So I have information about the error. Here we are, here we have the confusion matrix results. Here. On the other side, I have the instructions, so I have the context, right? Written. You cannot read, but I have them. On the other side, I have some pre-made templates. Okay? Templates. You did something wrong, you should have done A, but you did B. Okay? This is a template. You just need to fill. How do I fill it? With the confusion matrix results. Templates, confusion matrix, assembly instruction. I take everything together with the manual prompt and I put everything inside the ChatGPT. I need to interface Python to ChatGPT. Costs $10 for the API and it costs a lot of tests. My PhD is spending day and night on it. But what do I have? I have an automatically generated correction instruction. The text. Wait, I can't read. Text is useless. Text is useless for sure, but I do a voice synthesis, right? I transform something written into an audio rendering, right? And I give it directly to your headphones. So you hear what's wrong and you hear what you should have done. Error notification and reversal rectification. Of course, this is the implementation of the digital instructions. Case study, pump. Takes 1 hour to assemble that. Centrifugal pump, generic centrifugal pump. Kindly provided by the Alto Barbera from Landizio, our sponsor. Many components, look at there, right? The company owner took 10-20 minutes to assemble it. Me and my PhD student and another technician, even with PhD, 1 hour and a half. There is something wrong. These are the components, these are the tools. We know everything, we know the instructions because we defined them, and we started working. We trained the system, and we performed 2 errors. Okay? We did on purpose, right? One is the wrong component, and one is the wrong sequence, the wrong tool. So we did this. the system recognized the error, right? So we have the confusion matrix results, and we prepare the prompt, hypercare prompt. So it's manually, it's not automatic. Okay. You are given two attached documents, which are the assembly instruction for centrifugal fan, the error log, and your task is to generate concise, dyslexic-friendly instruction for the given error in this way. So I gave the prompt. Prompt, error, instructions in ChatGPT, which in no time, really, 3 seconds, generates an error log. No, sorry, generates, these are the error logs coming, these are the input, generates an instruction. Text. Yu Chen is my PhD student, so we used her as an experimental subject. It looks there is a small mistake in the assembly process. In this particular step, you took the wrong component. You should stop the current task, remove, replace. So these are the instructions. These are the instructions that have been subsequently.
Hey Yu-Chen, it looks like there was a small mistake in the assembly process. In step S6, you picked up the wrong component. Here's what to do to fix it. 1. Stop the current task. 2. Remove the drive shaft companion flange from the assembly area. 3. Find and pick up the correct component. Hex cap screw, big C26. 4. Thread the hex cap screw, big C26, by hand into the threaded hole above the supervisor. After you're done, double check your work.
All the supervisor needs to come, needs to check, needs to understand what's the problem, needs to tell you what to do, check if you are doing it.
Great. Keep it up.
This is much quicker. Now I'm showing this. This is for teaching purpose. The message can be much more concise, right?
Hey, Yu-Chen.
Hey. With and without this system. Look at the time. It's a big time saving. We're not getting it, but before you call the supervisor needs to come, the supervisor needs to check, and then you need to adjust, you need to fix, check again, and then start. With digital instructions, that is much shorter, right? I want to show you how it's done, because it's very convenient this way, okay? So here we have the instructions, here we have, this is the Python code, this is the camera, and it's in the assembly progress. Look at that.
Please prepare the following components. X-cap screw, big, C26.
Right? It tells you, because you don't know how to read. So everything is sound-based.
Pay attention. It looks like there is a mistake in the assembly process.
Mistake.
In step S6,
Right? Detected. Mistake has been detected here,
instead of
right?
the X-cap screw, big,
This is the
C26.
code running. This is the written instruction. You hear the digital voice
One stop the
instruction.
current task.
And this is
To locate the incorrectly
progress
picked
of this.
component. The
This is what you should do, right?
Or
This is
replace
what
the
you
drive shaft
actually
and the flange with the correct component. X-cap screw, big,
Now,
C26. Or thread the X-cap screw.
for neurodiverse individuals, especially those with dyslexic or reading issues, the voice is very important. You have different reaction to different voices. Right? If you hear your boss, you have a reaction. If you hear your mom, you have a different reaction. If you hear a person you don't know, you have a different. So, another interesting task is going to be, right, what's the right voice tone that minimizes your mental cognitive load? Right? I want you to do here with the voice of the Pope or the voice of Donald Trump, but I didn't. Still, the voice is very important. It reduces or increases the cognitive load. So what you say, giving the digital instruction can be completely cancelled or enhanced with the right voice. That's what we did. We are still working on this, and we are still also including different neurodiversities, logic, math, other things. And we want to integrate these with the collaborative robot I showed you before. Okay? So, I hope I wasn't boring to you. I hope I give you some interesting stuff. No? And, well, from my side, that's all. I thank you very much again for coming here during your holiday, maybe elsewhere. Maybe said you decided to come here. Thank you very much again. I'm here to answer all your questions. Thank you. Let's discuss, not only technical questions on the algorithm, whatever you want. We're not discussing. No one's watching us except the whole world by YouTube, but Professor.
The first part of your presentation, you presented the risk map and solutions that. In those scenarios that you presented, there are a time period which is different for each kind of risk and the prediction of those risks. Like mental risk, how can you enter to a system with a mental risk which can be predicted to have a different period of time to be presented by different person.
Clearly.
Like there are kinds of work. I know that you might have read the book of Christophe Dejoux about illness, mental illness that you can get in work. There are some kind of work that can promote mental problems, and there are works that can promote physical problems, which is different. If you can predict this, how can you confront this kind of risks with the legislation of work? Because if you know the risks of your work in a short period of time, medium or long period, how can you process this kind of risk in order to not to avoid that a person can suffer from this risk?
Okay.
Like a mental, which is in medium period of time. How can you work with this?
Short answer, modeling the risk priority. Okay? Risk priority can be modeled in one of our papers, but what we do here, much easier, that we measure only things that certainly can have an impact on the mental health. Look there, for example, here in this very approximate, very simple categorization, stress, other things that clearly have almost immediate, right? Then for long-term risks, like some kinds of stress or ergonomic things, right? These are long-term impacts, you have a priority modeling. We did, I didn't present the priority modeling because it's a bit complex and a bit boring, but we have a paper on that. Based on the priority computation, then you can set your corrective measure over short, medium, and long term. Short, medium, for example, short time you put the plugs on your ears so you don't hear noises. Okay, but this is not enough. Long term, so medium term is to insulate the sound of the room, or long term buy a machine that doesn't produce enough noise. Okay, so I have this. But to do this, I need to understand where the mental risk is higher, for which kind of operations. That's the only thing I can do. Concerning the legislation, there's nothing we can do. It's something that we can't move. The only thing is that I can measure something that certainly has an impact on your stress or some component of the stress and perform short, medium, and long-term corrective actions. If this morning you got a ticket fine from the police, they were in bad mood, right? Or if you had an argument with your wife, we are not able to do this. What we can do is to add one more block here, daily mood. what you need to do? You go to work. Today I'm in happy mood because I won the lottery. And you press some button and I add one variable, right? Fine. This will complicate a little bit the computational aspects, maybe give you a more accurate thing, but what we want to model here is things that are certainly have an impact on the stress that we can measure. If the machine has a leak of lubricant, it smells bad, your mental risk increases. That's the only thing we can do. Anything else? Are you curious about some other aspects?
Any questions?
Questions, suggestions? Yes, you would.
Have you considered using the last approach you showed for in airplanes? Because they have all the data in computers. Like you have a camera showing someone doing something, but airplanes they have all this stored in a place, so you can know that the pilot did something wrong, maybe, or there's a situation and you have to make some steps to correct this. I think it would be interesting for you to get this data from companies.
Well, the point is that, we need factory data.
That's what I'm saying. Maybe companies they have airplanes, they have this data like accidents or stuff.
Yeah,
that the pilots are supposed to do
share
something.
what they have. How do they share what they have, especially when involving people.
Yeah.
So for now, only thing we can do is to work on our students, volunteers, like you. You monitor yourself. You bring your brother, your girlfriend, and so we can increase the sample size.
Yes.
But in the factory, especially with people, and especially with neurodiverse people, in Italy you need to fill you need to fill 20 kilos of paper for authorizations. It's absolutely a nightmare. They acknowledge the importance. They ask us how to help them, but then they don't give you. So you know where I got some data from? This is very interesting.
Yeah, that's
From
what
China.
the data.
From China, I managed to get some data.
Yeah.
I don't know how they got them, but we got some factory data from China. Anything else? Well, ChatGPT, yes. LLM.
Think about research like this one, the problem sometimes is the accuracy of this generative information.
Yes.
We have some also
Yes.
cases ChatGPT already.
ChatGPT can be inaccurate if you don't give the right data or the right prompt. If you ask, can you tell me how that movie ended? ChatGPT will invent the answer. And if you tell them, look, this is wrong, oh, sorry, you're right, the main character dies. That's not true. So how do you avoid this? You give everything. Okay? Look, this is the other input, this is the instruction, this is the data, this is the prompt. In that case, the answer you get is always correct. Really always correct. Otherwise, if you need to correct ChatGPT, then you need to make sure that this correction remains in the database. Basically, the bottom line, if you notice some mistakes, some inaccuracies by ChatGPT, make sure you fix it and you store this correction. So you need actually to work on the software side, make sure all your interactions are stored. That's how you do it. But for ChatGPT, but strong potential. Now I showed you only the memory and reading problems. We are developing now, this day, we have deadline in a few weeks, for logic problems. When you have logic problems, you struggle in performing a simple assembly task. So in this case, ChatGPT will generate, integrating ChatGPT and Canva, generate flowcharts. If you see a flowchart and if you have visual cues, a light that tells you this is the right piece, this is the right piece, this is the right tool. Integrate ChatGPT, Canva for the production of flowcharts, and of course visual cues, and updating is in real time as you assemble or as you do mistakes. This can really help. The operator in with logic issues. We call it logic assistant. Soon will be available. And then there are other, we're also doing some experiments. I have a master student doing her thesis in England, in Loughborough. She's doing experiments for the attention issues. It's also very, very interesting. So we are exploring as many sides of neurodiversity. The real problem is that when you have neurodiversity, you don't have two people with the same issues. Everyone's different, literally, by diversity. And this is very exciting, but also very complicated, because you have reading issues, but your reading issues are different from his reading issues, right? You struggle only with long words, and he struggles with drawings, he struggles with the... We are trying to integrate, because I think that technology exists, technology is there, ready, mature, didn't show you any unknown technology. What you do with that to bring people who are born, right, with neurodiversity, bring them forward to reach the same efficiency of non-neurodiverse people, I think it's possible. Difficult, but possible. And possible with the tools we have now. Of course, if you ask my mom, former teacher, how to help neurodiverse people, she will tell you dim the light, don't make noise, this kind of environment design thing. If you ask my sister, she will tell you, oh no, you need psychological help, visit the doctor need to bring you to the path of psychological, so more human based psychological approach. If you ask my nephew, my niece, who are teenagers, they will tell you, oh, you need an app. And the app is the solution to the technology. We propose this. This is clearly an early stage, but I think the concept is there, the results are promising, and we are, I think we are on the right way. Alright, anything else from the public? Alright, I'll be here for the next days if you want to interact with me.
Students have some questions, any questions, please.
During the mentioned reduction step, how do you know that you are not losing some viable information?
All right, you don't know, but what you know is that by literature, you know that the hearing risk depends on this, and that factor, right? And that's, so you build a hearing risk based on the variables that certainly affect the hearing risk. And certainly means that there is the relevant literature. And that's the only thing you can do. That's the only thing. So you don't lose, don't look from that perspective, you don't lose information. You are building the information that you didn't have before. You're trying to quantify something that the doctor would tell you with natural language. You have hearing risk because you've been exposed to noise, vibration, and no what else, right? So, okay, the difficult part is to understand the knowledge base, build a knowledge base based on literature. The hearing risk can depend on this factor. The experimental results show that an exposure to over 8 hours to this particular number of decibels increase the risk by 50%. Right, you build this. Of course, all of this, the normalization must be exposure here. If the risks are for 10 minutes, the risk is low. For 8 hours, then it's long, right? So there must be a sort of fatigue factor that increases the risks. There is there too, trend like this. And you are building basically indicators. So you don't lose information, you are building information. You are transforming data into information. That's what you can do, really. That's what you do. It's a big work of literature. It can be assisted, again, by ChatGPT or any other LLM. This is the relevant literature. This is the indicator I want to build. These are the input. Can you find me the fuzzy inference rules that model this relationship best? I will give you some parameters that you then need to verify, because it's not yet reliable from this perspective. but it's all literature based and industrial practice based. Yeah. Sure.
Thanks for the quite nice presentation.
Good.
I think that, in my opinion, your research is very like multidisciplinary.
Okay, must be.
So, like, just philosophical question, like, what is hardest for you, like, for your research group, working on the technological part of the work, or on like the social things that you need to understand to apply to your work, or integrating both things?
All right, the most difficult part is to get these relationships quantified because they do not belong to our expertise. We are used to 2 plus 2 is 4, which is true for us, not in medicine, not in occupational health. So some of these relationships, they've been built, interpreting what we found in books, medicine, physiology, ergonomics. That was the most difficult part because programming is is difficult today, difficult tomorrow, but the day after tomorrow you manage to do it. So technology, you can hit your head on the wall for a couple of days, but then it's done. Here instead, if you change one number, you clearly get the wrong diagnosis, right? But how to mitigate this? Mitigate this by normalizing all the results in the interval. Where is it? Right? So, I don't really care if this is 0.32. I just care if there is a spike here. If there is a spike, then there must be something dangerous. If you model the fuzzy relationship right. Yes, anyway, modeling the fuzzy relationship still is, because we are still fighting with that. The most difficult part. Technology is just our daily job.
Okay, thank you.
Sure.
In the case of the risks that you have presented, how can you put in this equation the mental state of a person that comes to work today? Like I had
That's what I don't
a fight with my wife, and
That's
I'm
what I
not.
don't know.
How can you predict this kind of?
No, you cannot predict. You can add one more variable, which is self-assessed. Basically, when you come to work, you should tell the system administrator that today your mood is bad, 2 out of 10. But this is only you know. Only you know. Otherwise, what can I do? I can guess you look strange today. Maybe you are in bad mood, and then how I input this. No, the only thing that we can add the self-assessment variable for the mood.
But you can monitor, like blood pressure.
Oh yeah, that we can do. That we can do. But
Things like that.
what is that? I don't know if the blood pressure is because you argued with your wife or because you smoke 60 cigarettes per day, right?
Mhm.
I need also this kind. So the more information, the more data I have on your health, the more I can provide an accurate diagnosis, which should never be 100% accurate because there are personal factors. Not only you argue in the morning, but at work something is wrong, right? Something is going wrong, and your mood changes. I can detect because of your heartbeat or because of the sweating. The point is that I will never know the truth, right? I can say something that I want to know.
I'm saying that because once I went to a factory which made an assembly of machine tools, and they had a guy which was, I don't know the name of the operation is correct in English, racking machine bays. Okay? And the next day I was in the plant, I saw that the guy was not working with the racking of the machine bays. And I asked why he's not. He said that he had a fight with his wife, so he's very nervous today. So we decided to transfer him to make other kind of work in the factory. That's the first time that I saw a kind of interaction.
Correct, but you know this because he said.
Yes.
So again, self-assessment, right? That's important, but it's something we need to hope. There's no certainty. If you tell us, then we know and we can put in the system. If you don't tell us, we can guess some strange behavior. If you start shaking, if you start more nervous, it's still invasive, more difficult to detect, and still uncertain because we don't know.
But you could have different decisions to make, like you have the experiment where there is an assembly. That the guy that is going to make that assembly, he just got to know that his girlfriend is pregnant, so he's kind of lost in his work.
Yeah, I understand.
And something is not doing okay with him. The machine starts to correct him many times. That brings a stressful sentiment for the operator. Can you predict what to do in terms of helping this guy? Because he's not going to talk to his manager.
Yes.
What to do?
No, at the moment, at this stage of research, no. At the moment, the only thing we can do is to correct as many times as needed his mistakes. What we are trying now really is to build a sort of error history, which is personal but also collective, but nothing else. No, really, we can't. We didn't get there. The error history is, basic because look, so far you always do the operation number 9 wrong. Pay attention. Or look, 90% of the workers struggle with this operation. So this is the error history. But this kind of personalized mood or anyway stress, personalized stress assistant, we didn't get there. What we did is to break down the stress into 6-dimensional memory because they are the relevant to the manufacturing tasks. But no, we didn't get there. It's difficult. It sounds difficult task, challenging, beautiful task, but difficult. We can try. Let's see what we do. And no, because I mean, a mood-based correction that can be interesting. Mood detector. There are some examples of mood detectors that a colleague from China showed me for students during the exams. Okay, students during the exam, mood detector based on facial expressions. But that's only bad mood 30%, bad mood 70%. You are afraid, you are overconfident. No corrective action. Interesting. You do it now. Think. We will think actually. Okay. Anything else? Sure.
Well, self-assessment is related to self-consciousness and self-awareness. So how do you see reliability of this system integration?
There's no. I mean, how would you model it? Self-assessment, then your husband calls me and say, look, regardless what my wife told you, the truth is, and give me some different data, or the other. So there's no reliability. There cannot be. We are going into a field which is not more engineering, it's psychology, so I need to understand if what you tell me is true. Trying to make life easier for the operators and it's a very difficult task. Interesting. How to the reliability of the self-assessment. I guess there is relevant literature about that, but outside of my expertise. It's a big darkness over there. It's challenging. Gave me some interesting hints. Thank you. Anything else? Sure.
thank you for your presentation. The last paper, you are trying to improve the cognitive loading, I suppose.
Yes.
Yeah. But in ergonomics, there is a literature about the interruptions, especially in medicine and emergency rooms. They study the effect about the interruptions of the work when he is doing a task. And your approach is very interesting, but I was imagining...
Disruptive, you mean? You can say that there
the
are some
guys is
disruption
working, there is the machine, there is the sound, there is the material, and we need now a new input that is the
It's
sound.
true. It's definitely
And
true.
I would like you to know if you just study about this in terms
Okay.
of the effect in the long range.
Not the long term. What we noticed is that even for non-neurodiverse people, when you give the sound and at the same time you show a video of the correct instructions, the operator doesn't know what to do. So this is true. And we need to study, but we are still behind. We didn't get there. Anyway, the overload of input is a problem, as well as the underload. Okay? The underload when you are completely alienated from the class. These are two things that we didn't have time to study, maybe also the resources, but we have to, because sooner or later this is going to be a problem, research problem to approach. We didn't get there, honestly, no. But I acknowledge the problem. It's big. Thank you.
More questions?
All right. Thanks again. You're very kind. Very nice discussion with you.